Okay, hello everyone. So here are the solutions to the physics problems. The first one, we have these two masses here. Both of them are M, and they go over a pulley and hang like this. And yeah, this angle is 45 degrees, and so we want to find the acceleration after it's released. Okay, so this problem is just pretty easy to figure out. You just have to write all the equations for F equals ma, and then it's just pretty simple. So it's a pretty classic problem. So the acceleration here, a for this would just be mg minus t over m, where this t is the tension in the string. Because these are the only two vertical forces. And then since the string doesn't change length, since the string doesn't change length, the acceleration of m going in this direction, up the incline, has to be the same as this mg minus t over m. And since this tension is the same, it's also t, then it's t minus the backwards acceleration that comes with gravity. This would be, the force would be mg sine theta, because this is mg, and since we're only taking this component that points down the incline, so we have to multiply by sine theta again over m. Okay, so now it's pretty clear how to solve this. Mg minus t is equal to t minus mg sine theta. So then mg times 1 plus sine theta is equal to 2t. And this means that t is equal to mg times 1 plus sine theta over 2. So now, since we're just solving for the acceleration, the acceleration A we already found it for is mg minus t over m. So now we can just plug in t, and we get this would be equal to g minus g times 1 plus sine theta over 2. And this is equal to g times 1 minus sine theta over 2. And since the angle theta is 45 degrees, then sine theta is just equal to 1 over square root 2. So then we can just plug that in, and we get g times 2 minus square root 2 over 4. And so that is the answer to the first problem. Does anyone have any questions? Okay, then I'll move on to the second, where the second problem, we have this. We have 3 moles of an ideal gas that expands isothermally from 5 atmospheres to 3 atmospheres at a temperature of 0 degrees Celsius. And we want to find how much heat the gas absorbs. Okay, so that basically, the amount of heat it absorbs is just the work done, W. And this is equal to integral of P dV. This is probably something you should know. And so now from this, in this case, it would be from P1 to P2. This would be 3 atmospheres. The starting point would be at 5 atmospheres. So that's what we're trying to find. And since we know that from the ideal gas law, PV is equal to NKBT. So then P is just equal to NKB KBT over B. So then this integral would be integral of P1 to P2 n kb t over b times dv. And so now we want to, so since we have like dv here, then it would be pretty easy to integrate from dv. So then we can do this, nkbt over v times dv. This v1 is the volume at the starting position, and v2 is the volume in the final position. So then this would just be equal to nkb times t and then log of v from v2 over v1, since 1 over v integral, it's log v. That's probably something that you should know as well. And so then this is nkbt times log of v2 over v1. And so now we have this expression in terms of v, but we don't know v. What we do know is the two pressures at the start and the end. So how do we get this expression in terms of the pressures? We know that since it says that the expansion is isothermal, which means that the temperature doesn't change. And since PV is equal to nkbt, the temperature doesn't change. That means PV is constant. So then that means that V2 over V1 would just be equal to P2 over, would just be equal to P1 over P2, actually. Yeah, it would just be equal to P1 over P2. So then we would get this work W is equal to nkbt times log of P1 over P2. And so now we can just plug in all of the numbers that we have, and we would get, it would be something like 3 times 6.02 times 10 to the 23rd, and then times 1.38 times 10 to the negative 23rd, times 2.73, and then log 5 over 3. This is only for those who are interested. This above expression for the work is probably more useful. Where we plug in the numbers is only for like finding the actual solution answer to the problem, which isn't all that necessary. And if you plug this into a calculator, it should turn out to be about 3.48 kilojoules, I believe. So that is the answer to the second problem. Okay, does anyone have any questions about this problem? Okay, since it appears no one has any questions, then that's it, and thank you for listening.